quick break for people to stretch out their legs. Thanks, Gustavo. Over to you.
Thank you, Tom. So welcome back, everyone. So it's really, really my pleasure to introduce you to Martin Gastal. He is an engineer, well, a master in physics, actually, an MBA from CERN, the largest laboratory in the world dedicated to particle physics research. And he has been the manager of the area of compact muon solenoid detector, one of the two experiments involved in discovering the famous Higgs boson. So this, as you can imagine, it's really a challenge to manage such large facilities, and these are really, really long-term facilities that they require perspective on tests in throughout the life of this components and systems. So just Martin, this is the floor is all yours. There you are. Martin, can you hear me now?
I can.
Perfect. So I just the floor is all yours. I'm gonna shut my mic and my cam, and you can share the screen, and welcome.
Okay, hi. Thank you very much for having me. Can you see my screen properly?
We do.
Wonderful.
Yeah.
All right. So my
see your image. I don't see your screen. Sorry.
Why not? Dear, what's happening? Oh yeah. Hold on.
If you click the share screen, which is on the lower part of the interface.
Yeah, got it.
Super, thank you.
That should do it.
There it goes. Perfect. Now we see the screen. Yep.
What about this?
Excellent.
How's that? Okay, wonderful.
That's perfect.
All right. So yeah, my name is Martin. I've been an applied physicist at CERN for the last 17 years. I have to say it's the first time I'm giving a keynote speech remotely, so it's interesting. I'm a bit nervous. I don't have a very good record with video conferencing systems, so if it crashes, it's probably me in a way or another. What I'm going to do today is take you on a tour of CERN, and in particular, the Large Hadron Collider and the compact muon solenoids, which are part of a very large facility, our flagship project, in fact, dedicated to the analysis of collisions when two protons go against each other. These facilities, as was just said a second ago, are there for the long run, and therefore you need to design, operate, maintain, but also decommission them. And this is over several decades. On this first slide, what you see is our region. So you see Lake Geneva to the right. You've got Geneva Airport here, and this white line is in fact setting out the perimeter of the LHC, the Large Hadron Collider. This is a 27-kilometer ring. And as you will see, it's a fairly complex beast to manage. And what I'd like to do is try to show you the amount of through-life engineering culture that we've got in our DNA. So I'll first talk about CERN, introduce it so that you've got an idea of who we are, what we do. Also introduce the compact muon solenoid, so one of the 4 detectors of the LHC. And I have to say, I've been spending most of my life at CERN working on that detector. And then I'll take you through a few specific through-life engineering issues, and then we can go to conclusions and some questions, hopefully. So we like to say that CERN is the place where the infinitely large meets the infinitely small, because what we are studying, despite the N in CERN that stands for nuclear, what we're actually studying are particle physics. So these particles are extremely small objects, obviously, but the study of how they interact, how they're formed, this actually teaches us a lot about our universe. So something that is infinitely large. So what is CERN? Well, we are an intergovernmental organization based in Geneva. So we are like an international organization, a bit like the UN or WHO. We've got 4 pillars in our mission. The first one is clearly science. So we promote science, but also we carry fundamental research in particle physics. And the best thing that can happen to us is to make scientific discoveries of the type that took place in 2012 with the discovery of the Higgs boson. And when that happens, normally we hope to be associated with the Nobel Prize winners that get honored in Stockholm. So the picture on the right-hand side shows three very famous physics Nobel Prize winners that all three worked at CERN. That's, of course, the bulk of our mission. But we also try to give back to society. Being publicly funded, it's very important. And so we are consistently developing technologies and pushing innovation so that there is a return on the investment that taxpayers are making into CERN. One, of course, very famous example is the web. The web was created at CERN, not because we wanted to create the web, but because this was a tool we needed to develop to carry out our fundamental research. And I will show you a bit later, but we also have some stake in medical applications. The third pillar is training and education. In order to get the talent that we need to tackle the challenges of fundamental research, we need to bring promising scientists onto our project very early on. And that means maintaining a pipeline of talent that starts very early, as soon as high school, in fact. And even sometimes when we can, we train high school teachers, try to inject the passion for science and physics very early on. And finally, our fourth pillar, I think it's a bit like a social experiment. We are like a small version of the world. We've got over 110 nationalities on our campuses, with about 18,000 scientists working together. And that is quite unique, and good news that it works. And so CERN, it's a long story already. It started in 1954. At that date, in that year, we moved from being a council, so an advisory body, to a real organization able to build facilities, to hire staff. So this is really when the story of CERN started. And as I was saying a bit earlier, don't be fooled by the N in CERN. The nuclear research was something that we needed to advertise at the very beginning to stop the brain drain towards the US. But what we are doing is really particle physics. So who are we? This map shows our member states. So what in dark blue, you see what we call member states. So there are 23 of them, mainly Europeans, but you will notice that Israel is also part of the family. Then you've got, in slightly lighter blue, associate members. So these are members that are on the path to become full members. And there you can see extremely important stakeholders in science, like Pakistan, India, Turkey. And then you've got what we call observer countries, like the US and Russia, Japan. Again, extremely important stakeholders for our project, but they have chosen to remain, let's say, not automatically contributing to the CERN budget. That's why they have the observer status. So the way things work at CERN is that we get about 1 billion Swiss francs or dollars a year that pay for utilities. We are one of the two largest consumer of electricity in Europe. Of course, for personnel, contractors, tooling, but the bulk of that money goes to the LHC, so our flagship project, the Large Hadron Collider. The way this funding is distributed is very social. So it's a function of GDP, which means that the better your economy is doing, the more you pay into the CERN budget. That's for CERN, but obviously that's not only with 23 countries that we would be able to, 23 member states, that you would be able to attract more than 110 nationalities. The other mechanism is what we call collaborations. There again, it is a very exotic experiment, a social experiment. Let me illustrate that with an example. If a university in China not being a member state of CERN, wants to take part into our project, there is a very easy way to do so. Each and every country on the planet can have institutes, meaning research centers or universities, deployed on some project through what we call collaborations. Collaborations are essentially a group of scientists, of universities that decide to pool their resources together for mutual benefit. And this is all articulated around the design, construction, operation, maintenance, and upgrade of particle physics detectors. So these big detectors that are looking at the byproducts of the collisions taking place in the LHC, CMS being one of them. This is very important because having stakeholders from all over the world, of course, increases diversity, and we strongly believe this is also the best way to achieve the best results. So how many people are we? We've got 2,500 staff at CERN. We've got 600 fellows, so let's say postdocs and apprentices, to which you should have 500 students, doctoral students, masters and bachelor students. But the bulk of the manpower at CERN are actually what we call users, and users are people employed by their institute or university and sent to CERN. Cranfield is one of the latest additions to the CERN family, and so people affiliated with Cranfield can enjoy the status of user at CERN. So 11,000 of this category of personnel can be found at CERN on any regular day, to which you need to have 2,000 external companies. So on a good day at CERN, you will be, well, not these days, unfortunately, but on a, let's say, pre-pandemic days, you would be working together with 15,000 colleagues. This is a map of the world showing where we've got our scientific contacts, and you can see that, unfortunately, Africa is not so well covered, but we try to cover most of the globe. These are people who are not employed by CERN. These are people that are employed by universities and sent to CERN to work on our project. And you can see for the UK, we've got a bit more than 900 such users, Cranfield having a few, obviously. So what are we here for? Well, clearly we do fundamental research. So we try to answer the big questions. You mentioned in the introduction the Higgs discovery, the Higgs boson, and that was clearly one of the highlights of my career, to have the good fortune to be at CERN when this particle was discovered. It's, as you know, it ended up awarding a Nobel Prize to the two gentlemen on the picture, and the ultimate satisfaction for us was to be mentioned in the Nobel Prize awarding. And so you will see that in the text, the text mentioned Atlas, CMS as experiments, but also the CERN Large Hadron Collider. So you can already see that the communities of the experiments are as well acknowledged as the CERN staff who has been in charge of producing the LHC. Now we've got the Higgs boson, but this is far from the end of the story. There are so many questions that still need to be answered. We like to think of the LHC as a time machine because the kind of state of matter that we manage to reproduce inside our detectors, inside our colliders, is similar to what it used to be fraction of a second after the Big Bang. So it is a way to fly back in time and better understand the mechanism that are at the origin of our universe. Or the big questions are antimatter, not the angels of demon type of thing, but really antimatter in a sense that why are we here, since there should be as much antimatter as matter, but the fact that we're here, clearly this is not exactly symmetrical. Part of this research is done through a satellite that is on board the International Space Station, and the control room for that apparatus is at CERN, one of the CERN campus. The next big question will be dark matter. As you know, the universe is made of normal matter, but it's a very small percentage, only 5%. The rest is much more exotic, like 26% of dark matters and 69% of dark energy. Being able to spot, to quantify, to analyze that sort of matter would be a huge achievement for CERN. And to raise to the challenges of what that implied by studying this sort of or answering these sort of questions, there's no other way than collaborate to do that. This is why I was saying this is kind of an experiment, social experiment at CERN. We need all the resources we can get our hands on because the challenges are absolutely huge. And this goes through education. This is a picture taken, so not last summer, the summer before. This is a summer student program. So every year we try to attract 1 to 2 students per country around the globe, bring them to CERN for 2 months of hands-on training in high energy physics. So how does it work? Well, to put it very simply, essentially what we're doing is smashing protons together at the speed of light, but we do that 40 million times per second. So a lot of statistics, a lot of opportunity to produce the biparticles that are so exciting for us because they've not been observed yet. The basic mechanics is that you know the famous equation E=mc². So the energy when the energy at the collision point when the 2 protons get together gets transformed into matter, and this matter flies out of the detector. And this is what we are trying to analyze. It all starts to produce these protons in a bottle of hydrogen, and then you just kick out the electron and you're left with your proton. Before these protons can be in the appropriate shape to be circulating at the speed of light around the LHC, they need to be stacked together in bunches. They need to be accelerated in various stages. And every time that they go through a stage, they get the more adequate properties to be injected. And these different accelerators that you see here, the booster, the PS, and the SPS, these are actually a facility that dates from some time ago. As you can see, one of them is from the 60s. So this is the kind of time of operation that we're talking about at CERN. These facilities need to be built to last. Once the protons are ready to collide, they are going to do so in large detectors. So every 25 nanoseconds, 2 bunches in both beams will collide and will give rise to new particles. And these new particles will be recorded into one of our 4 detectors. We like to say that the LHC is the largest machine on Earth. If you look at, again, a top view of the region, this is the French-Swiss border. This is the main CERN campus, which is on both sides of the border. The second campus is exclusively on the French side. The acceleration process starts on the main campus, then it goes through a series of rings, and eventually it is injected into the LHC. And then you've got these 4 locations on the ring where the protons are sent head-to-head for collision. In order to keep the beam of protons onto an orbit that allows it to circulate around the ring, you need extremely powerful magnets, 9 Tesla magnets. These are superconductive, and these are the most powerful ever produced. You can see at the end of this picture a bend to the left. So this is just to show the beam line arriving at an arc and making it turn to the left. In order for the beams to circulate through the accelerator, you need extremely high vacuum because you don't want your protons to hit anything before they are meant to collide with the beam going in the opposite direction. You've got 2 beams, one going clockwise, the other one going counterclockwise. So the kind of vacuum we need to achieve is about the same as between the Earth and the Moon. So it's essentially what you would find in outer space. We also like to say that we have one of the coldest temperatures in the universe. This is because we need these very powerful magnets to be cooled down. The coils are made of niobium titanium, and these need to be brought down to 1.9 Kelvin to become superconducting. And we need that superconducting performance to achieve the power we need. And finally, you've got the detectors. So this is a drawing, so you can see the size of a human being. So we're not talking about a tabletop experiments. These are enormous apparatus that are buried underground. This is a picture of Atlas. So the experiment that was also, together with CMS, associated with the discovery of the Higgs boson. This is the CMS, the compact muon solenoid experiment. And just to give you a little feel of the sheer size of these objects, I've got here a little video. This is taken from 100 meters underground in the CMS cavern. You can see my colleagues going around the detector to carry out some maintenance operations. In the middle here, what you see is the beam pipe. So you have to imagine that the protons are one beam of proton going that way, the other one going the other way. But here you can already see the complexity and how integrated the parts of the detector are. These detectors, all four of them, get collisions to analyze every 25 nanoseconds. And so the amount of data that they produce is absolutely enormous. We're talking about 1 petabyte per second. So there is no way this amount of data can be either stored or analyzed. It needs to go through a very strict screening process to only keep the data that we want. But even then, the data is so enormous that we have to send the data in various locations. It cannot be done just on one site. So this decentralizing of the data processing led us to create what we call the worldwide LHC computing grid. And it consists of several tiers. So the tier 0 is CERN. Tier 1s are large facilities like at RAL. And then you've got the tier 2 that are typically clusters of computers at universities. This is the way data is analyzed and how the discoveries are made by sending data all around the world and collecting the results. Now, I mentioned this return on society. I mean, CERN is entirely funded by taxpayers' money from the member states. And so we thrive to try and give back as much as we can to society, on top of course, pushing the boundaries of human knowledge, which is beneficial for all humanity, but most particularly in terms of short-term impact. Sometimes, as often as we can, we release some technology onto the open domain. The World Wide Web is one such example, created at CERN, again, not because we were looking for it, but because we needed it. And another aspect of this technology and innovation, it resides in proton therapy. So this is the treatment of tumors in areas of the body where surgery would be too intrusive. So typically brain tumors. The idea that you use proton beam that will deposit the energy exactly inside the tumor and not affect the healthy tissue around, which is of course, the most important for that sort of condition. So that was for CERN. Now let me jump to CMS. So CMS is on the French side, quite far from the main campus, actually on the opposite side of the ring from the main campus. It is 100 meters underground. This is a depth that is higher than for Atlas because we are closer to the Jura mountain. So we had to go a bit further down. It consists of 3 shafts, 2 caverns, and quite a series of surface buildings. This is a picture taken of the CMS experimental cavern, so where the detector is meant to be before the detector was installed. And you can see this is a fairly vast space. And for good reason, because our detector, even though we call it compact muon solenoid, has a diameter of 14.6 meter, weighs 14,000 tons, so twice the weight of the Eiffel Tower. At its center, it's got a 3.8 superconductive magnet. So you are talking about a very big piece of detector, and clearly this can be seen on this picture. This is the CMS detector fully installed in the cavern in what.
So I think Martin's connection has just died. Let's wait for a second and see if he comes back. Absolutely impressive machine he was describing. Martin, can you hear me? Your connection just died.
Okay. Can you hear me now?
I can, yes. Sorry. You can continue now. I think the system is on again.
Wow, we're supposed to have a one of the best connections in the world. Sorry about that. Don't know what happened there. I don't know, where did you lose me? At what slide?
Just a second ago, it was less
Okay.
than a minute.
Okay.
Yes.
Okay, fair enough. So I was just saying that this picture is a good opportunity to quickly go through.
Can you share again your screen?
Oh, sorry. Yeah. Apologies.
Perfect.
Okay. All right. Let me try again. That one. All right. So yeah, I was saying that this picture is a good opportunity to explain the structure of the high energy physics detectors, because they all are fairly similar for a good reason. You have to think of it as a kind of an onion. So it's a series of concentric layers, and each of these layers gives you a piece of information about the incoming particle that we are trying to detect. So if you take a slice of that cross section and you look at it here, you will see that the first very most inner layer of the detector, which is made of silicon, has the job to plot the trajectory of charged particles. This is the part that you see here. The second layer has the job to intercept photons and electrons and measure their energy. The curvature that you can see here is induced by the superconductive magnet that is at the heart of the detector. The third layer is intercepting neutrons and protons. Again, you want to measure the energy and so on and so forth. The last layers are for the detection of muons. Muons are not intercepted because they interact very little with matter, but we can still get a trace of their presence. So the idea is that you've got this detector, and every particles flowing through it will leave a signature of its passage. And when you put all these signatures together, you obtain what we call an event, which is here represented in a 3D reconstruction. And by analyzing these events and comparing them against the current state of knowledge that we've got about how particles behave, you can detect what we call a bump or an anomaly. So when you are looking at a particular way particles behave, if you find enough evidence or enough statistics that something unusual or unknown is happening, then you might be on track to make a discovery. And of course, you need an awful lot of statistics to reach that conclusion, but that's how the process works. And so you don't need less than 5,000 people to do that. We're about 5,200 and something collaborators in CMS. This is spread across 55 countries and gathers altogether 239 universities or research centers. So you can see it's a very rich network that we are activating in order to bring new skills and talent and creativity into our projects. Just in the UK, I listed a few of our universities, and of course, Cranfield is one of the latest edition. We look forward to having more Cranfield collaborators deployed on our projects. So now, let me give you a few examples of practical through-life engineering in our project. The first thing, I think you got the message, is that the project cycles are extremely long. I showed you a machine that was built in the 60s and is still in operation. But even if you look at detectors, the CMS detector was designed in the 90s and was built late 1990s and during the year 2000. The first time the detector went online, so taking collisions, making data, was 2009. We're now in 2020, and we certainly hope that the detector will still operate for another 15, 20 years. So at the design phase back in the 90s, we had to think about, of course, the construction and the installation. That was relatively short term, but we also had to foresee upgrade, maintenance, and unfortunately at the end, decommissioning. But this spans over such a long time that it's almost several generations of scientists working on it. So the first very big decision that had to be made from a long-term engineering point of view is where do we put that organization? So, because in the end, okay, Geneva is super nice, I'm not complaining, but one might ask, why in Geneva? Why not in a place that is maybe less densely populated or more central to Western Europe? Who knows? Well, there is a very good reason for that. As it turns out, the geology around Geneva is ideal for tunneling. If you look at the picture on the right-hand side, you see the lake here, and we have this yellow area, which is essentially sandstone that is squeezed between the Jura mountain and the Alps. And this is a very nice, stable, homogeneous layer of sandstone. So that led us to, let's say that it's allowed us to do a lot of tunneling and also to create caverns in a very nice and reliable way. Here you can see a TBM in action. This is for one of our tunnels, and these are pictures taken when we were excavating the caverns for the LHC. And having this ability to expand your tunnels to create new caverns is super important because CERN keeps it expanding. If you look at the LHC, as I said before, various steps are required before we can have proton beams circulating into the ring. These different steps are linked to other accelerators. So you got the booster, PS, SPS. But if you go back in history, each and every one of these accelerators was used for a different purpose. Once an accelerator reached the limit of its discovery potential, it was then transformed into an injector for the next generation of accelerator. So this is how you end up with a chain of injectors, eventually bringing the beam into the LHC. And all these parts need to be thought through so that they can be interconnected as CERN grows, because the only way to keep discovering new particles is to keep getting or building and operating more powerful accelerators. And in a circular accelerator, the only way to do that is to have rings with larger diameters. What we like to do in order to avoid losing knowledge and losing promising scientists is always to have periods of what we call physics, meaning when we are taking data, when collisions are taking place. So we'd like to have the minimum amount of dead time between two physics run. But that doesn't always work. In the future, what we would like, so now we are in the LHC in operation, so you see somewhere again, another few years, let's say, we are already, while we are now in operation, we're already building the next generation of accelerator, which will be the high luminosity LHC. And this one is meant to go, as I was saying, 2035, hopefully 2040. And by then, we certainly hope to have the next generation of accelerator. This is to avoid that losing PhD students, postdoc that will come, let's say, that will be looking for new data to analyze. And if we are not producing data, then of course they don't have the necessary material to do their PhDs or their postdocs. So that's the theory. Now, it doesn't always work. As you can see, the gap between the end of the LEP, which was the accelerator preceding the LHC, that was using the same tunnels, but was accelerating electrons instead of protons. And there, the gap is pretty significant. It's almost 10 years. This is, at the time, we were hoping that this gap would be much smaller. And so there were some very clever plans to try and have both accelerator in the same tunnel so that we could minimize this dead time. But that clearly didn't work. I think the technologies are shifting so quickly, it was very difficult to do that. Now, hopefully we'll keep on growing, and the next step for us would be to build, whenever our member states feel it's appropriate and have the money, a 100-kilometer ring that will be using the LHC potentially as, again, a new injector. So we keep on growing. And so the region, again, is most suited for that, because even if we go to a 100-kilometer ring, Okay, granted, we'll have to go through some limestone, but mostly we stay in stable and fairly predictable layers of soil. Now, because we are always looking at several generations, or let's say to make the best out of the civil engineering structure that we build, when designing the LHC, we are already looking at 2 accelerators within the same tunnels. You're reusing the tunnels and the caverns. So the idea is always to start with an accelerator accelerating electrons. And once we have exhausted the discovery potential of an electron machine, then we switch to protons. Protons being heavier, they will deliver more energy at the collision point. So you potentially unlock more new processes that may lead to the discovery of a new particle. This is for circular colliders. We are also looking at linear colliders. So there, the idea, what's appealing about the region is that you can phase the construction. So you can start with the first linear collider that has a limited range of energy. And as it becomes appropriate and affordable, then you can increase the length of your accelerator. There again, all these things need to be planned well in advance. Well, again, through life engineering comes in through there, because you absolutely need to have foreseen the walls, all the different stages leading to the accelerator that you need. That was for accelerators, but in fact, the detectors have almost the same process. When beams collide at the center of the detectors, a lot of radioactivity is produced. And this is extremely aggressive environment for essentially all kinds of material. Metals get activated. If you've got electronics, the gate oxides get damaged. So even when we were designing the detectors in the 90s, it was clear that we were going to have to replace large parts of the detector at some stage, because the radiation damage was going to become too much. And that's what we're going to do in 2024, let's say, where this cantilever part of the detector will be replaced by a new one. So yeah, it works. So this is not a trivial operation. You need to remove an object that is about 300 tons underground, and you need to handle it as a radioactive object, because it will be fairly activated, having run in, I've been operating around collisions for a certain amount of time. And then it has to be replaced by a completely new object. And we certainly we need to keep the disk on which it is attached to. So there again, the bolting, all the mechanism to link the new object to the old disk had to be thought through, integrated. And at the design stage, back in the 90s, we had to, sorry about that. We had to make the best and build in the best flexibility into the object that we were installing. This is something we have for many other parts. When you talk about electronics, for example, the ASIC that were produced in the initial detector are obviously not available any longer. So in the way our electronic systems are being built, we also had to foresee how to completely refurbish these systems as the technology gets better. And this is quite hard when you're in the 90s to think, oh, okay, what kind of component will I possibly be able to use in 2020, 2025? So this is something that we have been trained from the onset to think about and to factorize into our design processes.
Martin, your time is coming to an end in a few minutes. Oh, great.
That's my last slide.
Perfect.
Yeah. All right. So just to summarize, so yes, through life engineering is in our DNA, just because we have to, because our projects have such long life cycles. This applies to our accelerators that we always try to transform into injectors for the next generation of accelerators, but also for our detector facilities. The real challenge for us is always to try and foresee the kind of technology that will arise 20 years from now so that they can be integrated into our systems. And this is made increasingly challenging by the radio protection requirements. The longer we collide particles, the more activated the detector gets, which means in turn that the more difficult it is, or the more constraints are put on us in terms of access, in terms of the operation we can do around the detectors. Thank you very much, and I hope you enjoyed the tour. I can only invite you to come and see for yourself, because I mean, let's be frank, this is done with your tax money, so you ought to take a closer look at it. Not now, unfortunately, we are in lockdown, but hopefully this is just a phase, and on a regular year, we get about 70,000 visitors in CMS. So I hope that in the future, you will be one of them. Thank you very much.
Thank you, Martin. It's a fantastic presentation and very, very interesting subject that you discuss. We have time for one or two questions, and there's one on the Q&A actually, which is related to the data problem that you mentioned. You mentioned how much data you record every second, but then the question raised there is, how do you decide what the data that you keep?
Yeah, that's a nice one. So in fact, there is no recipe. That's the simple question, because of course we can be looking for something specific like we were for the Higgs boson, but the truth is there are a lot of things still to be discovered around there. So the way we filter data is that we look at the data coming from the detector and compare it to models that predict how the detector would signal the presence of this potential particle should we see it, and then we compare the two. So in real time, almost in 6 microseconds, we're looking at the raw output of the detector and compare it with the various model that we've got stored inside our systems. But one might ask, what if you have not thought about everything that can possibly come from these collisions, and therefore these potential particles have not had their signature loaded into your filter? Well, that's quite possible, and in that case, we're actually throwing away valuable data. So that's the almost philosophical challenge that we had ahead of us. We are not sure what we're looking for, or let's say we know what we would like to find, but maybe there is something else we haven't thought about. But since we haven't not thought about, there is no way that we can keep that data as it comes, because this is all online. We can't possibly store all this. The other thing is, if your filter is too selective, so you put too much constraint on your filter, you run the risk of throwing away data that would have been valuable because you put too much constraint. On the other hand, if your filter is too, I don't want to say loose, but let's say accepts too much data, then you are submerged with data, and it's not humanly possible to analyze all this. So it's always a very fine line. The filtering of the data coming from live from the detector is keeping our DAQ colleagues extremely busy.
So it's a fantastic example that you gave. So essentially, your results depend on your digital twin model, which is the data you're going to compare so that you know what to store. It's very, very interesting. Excellent. Is there any other question on the room? You can raise your hand or post a question on the chat. So I do have a question in between. So it's a fantastic engineering challenge that you describe. Now, as you said, there are so many risks to people that I imagine that you have a very strict certification process for each component and each system. How do you deal with the legacy of that certification as you go from decade to decade and you have new technologies to certify components?
So normally, the way we split the load of these tasks is by community. So one community, so a group of institutes, will be in charge of the upgrade of one part of the detector. And so these institutes, these universities get together and collectively decide on what are going the quality criteria that will be applied from one generation of system to the next. But this is an extremely it's a careful and intensive process to make sure that you are, when you're shifting from one version of a system to the next, because the technology got better, that we are not compromising as you said, the legacy, that it's not compromising the components that are remaining from the previous generation. This is the way the collaborations work, is that we try to decentralize as much as we can so that the load can be shared. It is not let's say, a governance model that would work in industry, I'm afraid, because there you're really trying to mutualize the ideas and resources. And so, in fact, when an institute decides to take responsibility for a new component, this is the only mechanism to ensure that this is going to be a success, is the public commitment made by this institute towards the rest of the community. And this is it's a bit of a altruistic type of conduct, but this has been extremely successful.
Oh, that's really good to hear, and it gives you faith in humanity. So if there's no other questions, and we are running a little bit late, so thank you, Martin. It was a fantastic talk.
Thank you very much for having me.
I'm sure everyone enjoyed this.
Thank you very much. Bye-bye.
All right, so I think we can go to the next keynote today. Oh, here you are, Sam. And this is delivered by Professor Sam Turner. He's the Chief Technology Officer from the High Value Manufacturing Catapult. And Sam, the room is yours. You know how to share the screen, right?
Yep.
We're all in the back listening to your talk, so welcome.
Okay, great. Thanks, Gustavo. Good afternoon, everybody. Pleasure to be with you this afternoon. So as Gustavo says, I'm the Chief Technology Officer at HVM Catapult. For those who don't know us, we are a network of manufacturing innovation centres across the UK, 7 centres, supporting industry and developing growth in the UK manufacturing sector through technology innovation. For a second, while I pull up my slide set and share screen. So I'm also a past chair of the UK TES Council, and if I just go to full screen mode, and within HVM Catapult, we have one of our strategic objectives is looking at driving the uptake of through-life engineering services. And we're also very much focused currently on the roadmap to net zero. So I'm hoping, Gustavo, you can now see the full screen of my presentation pack. Let me know if there's any issues with that. So I'm going to talk to you today about the role of TES in addressing the net zero challenge. So net zero by 2050 is a UK pledge. This is, of course, a global challenge. And whilst I use some UK examples, I think the argument here is very much relevant for all of us across the globe and the wider TES community. But I'm going to start with the pledge that was made by the UK government last year to be net zero carbon emissions by 2050. And this was the wording used by Chris Skidmore, who signed the pledge. It's quite a commitment. And within here, whilst clearly it's a noble thing to do in setting an example and some leadership in working towards zero emissions, within that pledge, there's also a desire to look at how we can seize economic opportunities of becoming a greener economy. And I believe there's a really clear role for the through-life engineering community to step up to the fore to both help to deliver net zero by 2050 and also to drive growth, prosperity, I would say, rather than growth. So if I start by looking at UK emissions, this is from a study released from Bayes in 2015. So the data is always lagging a few years behind, but it's probably still representative of where we are right now. And you look at the emissions nationally breaking down to a number of chunks, transport being the biggest, power and conversion, buildings and heat, industry, land use, which includes agriculture and agri-tech, fugitive emissions, waste, and others. So transport and power are huge parts of this overall challenge, and buildings, all of which are built on developing large engineering solutions or infrastructure. And to address the target of net zero emissions by 2050, there's not yet a strategy in place to address this, but you've got a number of sector groups looking at how we might do that. We've got the Committee for Climate Change. We're making suites of recommendations. But there's an opportunity for industrial leadership, particularly for those industrial emissions, which actually rate somewhere between 15 and 30% of our total emissions, depending on how they're accounted for. Because arguably there's some industrial emissions associated with the other blocks. And also these are territorial emissions only. If we start to consider our consumption-related emissions, so this would be emissions related to goods and services produced overseas but consumed in the UK, which arguably is the more responsible line to take, then actually the industrial-related emissions are much greater. If you think about emissions embodied in goods and services provided from overseas. So how can we influence those and start to address a net zero solution? So the engineering challenge to get there, it seems clear that many engineers will have a key role to play, perhaps in some of the community who may be seen as polluters, but in addressing, many can articulate the need and the challenges, but it's likely to be engineers, the engineering community and scientists that will address and deliver the solutions that address net zero. So looking at those major emitting sectors we just looked at, clean energy is going to be a huge part of that. Things like offshore wind, arguably nuclear to have a role, advanced nuclear modular reactors, decarbonisation of transport, whether that's electrification or hydrogen. We've seen recent architectures being released by Airbus for the future vision of aerospace, but automotive, rail are going to be huge parts of that, electrification and fuel cells, the front runners. Sustainable buildings, so decarbonisation of buildings, and already with there's a lot of work starting to look at through life operation of buildings, not just the design phase, but how they operate through the life cycle and end of life. And of course, sustainable manufacturing. So it's not only the engineering solutions that deliver net zero, but it's the embodied carbon within them that must be addressed. So as we can engineer solutions that reduce our life cycle contribution, we need to think about the embodied carbon within them. And I'll use an example from one sector, which isn't a sector most obviously associated with life engineering traditionally, but it's one that most can relate to quite clearly. So we look at automotive as an example sector. There's a range of studies out there, again, that will give you a range of emissions, but the one study from a group called Small World Consulting, recognising there's up to 40% of emissions per mile for a traditional internal combustion engine vehicle are from the design and manufacture process for the vehicle and for the fuel production. The chart on the right actually came from TNO, referenced by the European Environment Agency, so it's another recognised data set showing a slightly smaller embodied emissions for internal combustion engine, petrol and diesel vehicles, but still significant. And as we move to renewable electricity or electric vehicles, depending on the energy source, the actual embodied carbon from manufacture of the vehicle and fuel systems becomes the bulk of the emissions per mile. So this leads us to see that decarbonisation of transport and energy is not enough. And we need to look clearly at the full life cycle emissions from design, manufacture, in-service and end of life. And life extension will greatly reduce the impact of those emissions. So the emissions here for renewable electricity vehicles are assuming similar usage cases to those that we see currently. So one thing that's still maybe in the near to mid distance for automotive is mobility as a service. Now, there was a report produced a couple of years ago by the TES Council, or what was then the EPSC TES Centre, with HVM Catapult, looking at scenarios for mobility as a service for automotive. So that chart where we saw about 70% of the embodied emissions being related to the life cycle, so the embodied carbon for a vehicle or the battery system. That changes if we move to mobility as a service, where we see life extension and utilisation going up drastically. So one of the things that's drawn out in that report was that if we move to this MAS scenario, where we're looking more servitisation of vehicles rather than individual ownership, we'd expect over 50% usage rates of vehicles, and therefore the need to design and engineer those in very different ways, effectively using through life engineering services principles to design fleets of vehicles. Now, for now, through life engineering really targets the higher value asset class, but this just underpins the point that using a through life engineering approach, maximizing utilization and maximizing or optimizing utilization, should I say, and optimizing the life extension will greatly impact the overall carbon emissions through the life cycle of any engineered product, and will reduce those embodied emissions from the design phase. So coupling that life extension of a through life engineering approach with manufacturing efficiencies as well. And here we would look in principle at improved manufacturing processes, use of clean energies throughout the manufacturing life cycle and in service, and use of lower impact materials. These all come into play in the design phase, as well as through the manufacturing life cycle of any high value engineered products. And the principle, one of the principles that is likely to underpin the transition towards net zero is the circular economy model. Now, not to say that circular economy is a means to improve resource efficiency, which will help us in reducing emissions, rather than being the underpinning principle for net zero. But by looking at a circular model where we move from the linear economy of taking resources out of the earth, producing, consuming or operating an asset, and then going to waste, moving to a system whereby we design and build for the full life cycle and looking to recycle and reuse materials rather than go back to natural resources. Through changing the way in which we design, build and operate these assets, there's an opportunity to impact 80% of the environmental emissions at that design stage. And if we think about breaking down the manufacturing and operating life cycle into a more linear process, this is an example that looks at the various steps in that manufacturing through to operation life cycle. So as the high value manufacturing catapult, we're thinking very much in this kind of framework. And we can go from a linear process that starts with raw materials extraction, convert that into something that is more circular, looking at recycle of some components back in, or re-engineering components potentially back at that component manufacturing stage, and reuse of materials back to materials processing. So designing for materials that can be recycled, reused, designing for components that can be upgraded or re-engineered, but essentially designing for extended life and optimized performance through life, and design for end of life can have a huge impact. And these examples here, we may look at anything from an aero engine fan blade, for the TES environments, the higher value assets, and you can think about how we produce those in such a way that we reduce material usage. So there could be efficiency in factory. There may be two different ways to look at machining or casting of a component where the methods that could optimize for energy and material usage rather than just optimizing for cost. So in aerospace, there's a term often used called the buy to fly ratio, where it's not uncommon to have from raw material stock, only 20% of that stock that is bought goes into flight. So material efficiency is a big opportunity to look at through this life cycle. So that's talking in general terms about embodied carbon emissions, the manufacturing life cycle, and circular economy. Now, this is highly compatible with through life engineering services and thinking about where the two can come together. So we think about the assets and infrastructure that will deliver net zero, thinking about those big sectors of the emitting economy. And I imagine for other nations, these are probably pretty similar to the UK, maybe a slightly bigger industrial footprint for nations with a slightly healthier balance. But clearly, growth sectors like offshore wind, programs to put in place new advanced modular reactors, next generation zero carbon flights, looking at hydrogen as an energy vector for transport or heating, electric vehicles and fuel cells and green buildings. All of these sectors that are likely to deliver the solutions are highly compatible with the TES value proposition. So this is the TES value proposition as recognised by the UK-based Through Life Engineering Services Council. The TES will, familiar to most of you, I'm sure. So TES will increase the in-use value and reduce the in-use cost of long-life engineered assets to the benefit of the user and provider. So that is to increase the availability, continuous function and utility to the user, and reduce the burden of long life engineering assets. That burden is normally thought of in cost terms, but we can also think about the burden in terms of life cycle emissions. And it seems clear that a part of that TES value proposition to the wider community is to reduce the life cycle emissions of long life engineering assets. And as with that automotive example, over time, the definition and boundaries of high value long life engineering assets may change if you move to mobility as a service or other servitized asset classes. So the TES value proposition is not only compatible, it's probably at the heart of delivering the net zero intent for the UK and globally. So the TES Council have done some mapping of which sectors are actually most compatible with TES, the TES value proposition. And this was a fairly simplistic model, just looking qualitatively at where various sectors sit. And within there, we identified defence, aerospace, rail, the energy sector broadly, so renewables, nuclear, infrastructure and transportation as those target sectors. And again, these are the sectors in which we have to see significant investment, re-engineering, new products and growth to drive down transportation, energy and power, and construction-related emissions. So there's a huge opportunity for TES to be part of the answer to delivering net zero. So look at the TES framework that was produced through the PAS 280, something that the TES Council helped to bring into being. We've got these two principal axes of the TES framework. So we've got the kind of life cycle execution processes that develop, prepare, utilize and retire of the assets, which fits very well with the life cycle approach articulated already around circular economy, or the mapping of the sort of manufacturing extension of the life cycle. Then the TES value streams around convert, avoid, contain, recover. And if you look a little bit deeper at those value streams and the stages of the life cycle, these are incredibly compatible with sustainability principles and the net zero agenda. So at the development stage, looking at the concept development of major assets and support solutions, manufacture and preparation support, operation, retirement, end of life and repurposing of those assets. Opportunities for upgrade, not only repair, for life extension and optimization of performance. Optimization here again could become, one of the optimization criteria could become lifetime emissions as well as cost. So how do we drive forward this TES agenda that is compatible with or underpinning, arguably, for the net zero objectives that we see globally? So one way to do that, we have the opportunity in the UK, the fact that the commitments made by government are very much national government commitments. We don't yet have an obvious strategy in place that had been formed by a number of industry and government and sector bodies. There's a chance to drive this, the TES uptake, I think, and the TES solutions towards sustainability and net zero through procurement programs. So much of the assets or infrastructure we've talked about are going to be government procured. Certainly defence assets, not obviously associated with sustainability normally, but actually with huge amounts of potentially large emitters throughout the life cycle. But certainly look at the energy infrastructure, whether that's going to be offshore wind contracts with agreed minimum base rates, whether that's going to be nuclear energy, but also our transport infrastructure. So programs like HS2 are already underway, but there's going to be other major regeneration programs in terms of rail networks, road transport infrastructure, an opportunity for government procurement, not only to specify requirements around embodied emissions throughout those life cycles, but also to embed requirements for operation to a TES business model, which should be absolutely compatible with objectives around optimizing value for the taxpayer and also driving reduced emissions throughout the life cycle. So TES is a means of reducing life cycle emissions and global emissions. The TES principles absolutely underpin those. And there's an opportunity to catalyse this TES ecosystem, domestically certainly, through government procurement programmes. So there's a requirement here, I think, to work as a TES community, as leading industry sectors across the sectors that we identify as high value engineering assets that are all going to be delivering solutions towards net zero, to come together and really clearly articulate the role of TES in delivering these solutions and ensuring that we can start to procure on a through life basis, not just on a point of sale contract. Now, some sectors are already a bit further ahead on this. I think, in defence, this is probably at the forefront. But can we do the same across larger construction sector, transport infrastructure? We know the Department for Transport are looking at how they can decarbonise the transport infrastructure for the UK and looking at innovation programmes and ideas that can help support that. The TES community should step up to the fore to deliver those. So the TES Council vision for the UK, this has a bit of a global and domestic view to it, but a vision or an expectation that over time that the TES becomes a dominant global business model for delivery of long life assets. It seems to be a logical outcome that because of the value proposition just on a cost and performance basis, never mind the sustainability benefits, that TES will over time become a dominant business model working across that development, prepare, utilise and retire life cycle. We believe that we can build a community in the UK and with international partners to lead in this competitive marketplace. It certainly isn't down to one nation alone. And the mission of the council was to build an ecosystem that ensures that we've got the skills, the technologies, the supply chain, the regulatory frameworks that will deliver world-class TES solutions. So in pairing the net zero commitments and the obligations of government, the required infrastructure build that's going to be needed to deliver those net zero commitments, and the obvious role that TES can play in delivering and meeting those commitments, we can start to drive this ecosystem, partly stimulated through government procurement programs, as well as through commercial activities in other markets such as transport. So how do we build that TES ecosystem? Some of the key aspects of that we've identified as the TES Council. Three of these are clear sort of working groups for the council around skills and workforce, standards development and business models, really building on the Path to 80 framework which could see further standards, but certainly provide a handbook and a guide how to TES practitioners taking up TES business models. Professional services, we recognise there's a need for legal, contractual, insurance, financial services to understand and operate TES business models. Recognising perhaps capital access to capital may change, capital flow may change if we're looking at companies down a supply chain of traditional manufacturers used to building at volume or batch volumes, who would then be looking at supporting through life service contracts. But importantly, the technology as well. So how do we make sure we have the underpinning technologies that would deliver a TES ecosystem that are compatible with the through life engineering and net zero requirements? So one of the great achievements in the UK recently and supported in part by the TES Council has been the launch of the level 7 apprenticeships for through life engineering services. So a number of universities with offerings in place. Here at Cranfield, of course, really pioneering with the TES Specialist Master's Degree Apprenticeship. That was a real landmark and point of pride for the council. And we're growing the community of TES practitioners and leaders coming through that apprenticeship program. So that's a really important landmark. How do we extend that and build on the skills and workforce in terms of the volume and reach from boardroom leaders and decision makers really understanding the principles of TES and the value proposition? Some of those leaders will come through the existing apprenticeship programs, but how do we support the incumbent leadership to understand the opportunities, but also how do we make sure we have the training and skills in place for shop floor engineers if they're working in a manufacturing environment, and field engineers who are supporting maintenance, grade and operation of high value assets. And also, so this breaks down, broadly, there's business and technical skills to be supported. But for the technical skills, which technologies do we need to address? And this is where the area of the road mapping comes into play, really, and building roadmap that not only delivers technology, but also workforce requirements and supply chain capability. So we have a terminology we're using with partners now across the HVM Catapult around the three-legged stool of capability. So we recognize that capability is about workforce, skills, technology and technology innovation, and supply chain capability. We need to build all three of these. But I'm talking now about how do we start to build a roadmap for TES that underpins the sustainability agenda. So the technology roadmap has already been some work undertaken through the TES Council and support from HVM Catapult. And we build this really around the TES value streams of avoid, contain, recover, and convert. And mapping the functionality or the actions required at each stage and looking at the technology, so not technology requirements, apologies for the typo there, that are required at each function. So this is rather a busy slide. I could leave this up for 10 minutes for you to digest. It's really an indication of the work that's been undertaken, the approach for now. And there's much more that sits behind it and underpins it. But really here we're looking at some of those value propositions here, the recover, contain, avoid elements with convert cutting across the top. And then looking at the data-driven cycle of data, insight, plan and act. So this was looking at some of the digital elements of technology that would underpin the TES roadmap. There are many others that build upon this as well. And then breaking down the avoid cycle into functions around design, manufacturing, usage, contain, breaking that down into timing and focus, recover, looking at move, access, inspect, repair, replace, and replenish. And each of these boxes, we've got to identify what's the action or functionality that we require technology to produce to deliver these requirements. So there's very much a digital flavour to this. Is the first pass we started. And clearly digital technology in terms of IoT, AI, prognostics, building sophisticated and reliable and robust models that can help us to predict lifecycle performance are going to be at the heart of this. Because a big part of this TES value proposition is going to be about those who create value in TES, we believe are going to be those who are best placed to own the risk and exploit that opportunity through having greater insight, intelligence into how to design, operate, predict the lifecycle performance and service high value assets throughout the lifecycle. So clearly digital technologies play a huge role in there. But alongside those are going to be crucial technologies such as looking at materials degradation modeling, automation and service access and maintenance, looking at novel manufacturing methods that may work on flexible and lower size batch sizes, potentially upgrading, evolving over time. And one of the advantages we may have the TES life cycle as well through this data and insight cycle is looking at if we're going to have access, having access to the data relating to an asset's performance in service, coupling that with the data that relates to an asset's or components manufacturing experience, and feeding that back to the design stage is going to be incredibly valuable. So linking this digital thread backwards, if you like, from end of life, operation in service, manufacture and design is going to create great opportunities. And if you imagine from a manufacturing perspective, which is often the one I start with, the current position we have, which may seem crazy in future years, that we manufacture high value goods to this binary tolerancing. The component is either good, it's in tolerance, or it's bad, it's out of tolerance. The data that we have available to us now, or the data that may become available as we develop these capabilities, technologies and skills, will give us much more richness about the experience and the qualities of an asset in terms of its surface finish, its geometry, its material integrity, which can then be related to how that particular component or asset performs in service, meaning that can then feed back to iterate the design and manufacturing specifications of next generation components. So these are just some of the ways of which the digital technologies will inform and accelerate and provide competitive opportunities to TES practitioners. So I'm not going to go through the whole of this map of functions, but if we go down the next level where we've got the actions and requirements here, we can then start to look at the technologies that underpin those. So in this example, I've just drilled into the manufacturing requirements. So looking at the action plan insight data, we have a number of technologies that we believe will meet those actions, and then listed the kind of underpinning pockets of technologies that are needed to develop those. What we've not yet done is start to convert that into a roadmap that benchmarks where we start now with the technologies available to in the landscape and their utilisation, or where we need to get to realise a future state with this digital thread and the associated technologies that will deliver the TES landscape. And I expect we'll see in those roadmaps and requirements more explicit reference to optimization for through-life emissions and material and resource efficiencies. So coming back out from the TES environment through the HVM Catapult, we've been looking over the last year or so at a number of different sector roadmaps and opportunities for reducing emissions, for driving a circular economy, looking across a range of high value and broader manufacturing sectors from food and drink and pharmaceuticals up to energy and aerospace and automotive. Through that investigation and road mapping, we recognise that through-life engineering is a huge lever to drive towards net zero, and will be should be a fundamental part of any strategy or technology roadmap to deliver net zero ambitions in a sustainable engineering community. So where does this take us? Really, this is a call to arms as a community to position through-life engineering services at the heart of the green recovery. Can stand side by side with sector bodies and with government, and working across industry, academia and RTOs to develop a TES technology roadmap with clear innovation priorities that will enable the rapid delivery of the solutions that are required to deliver net zero in a way that they are designed, manufactured, maintained, and end of use, end of life management that delivers the net zero ambitions and delivers a sustainable economy. So if we start to include through life emissions as an overt optimization criteria for some of these assets, which I think will be a requirement for transport sector and the energy sector explicitly, even if it's just from a consumer pull, never mind from a government set of requirements, we're going to see a much closer coupling, I believe, of the role of through-life engineering services and the sustainability agenda and the net zero targets. So we need to work across industry, government, the research and innovation community to build a clear roadmap and to prioritise and launch the programmes that will build that domestic and international through-life engineering services capability. So that's the end of the presentation, the talk. You can contact us through HVM Catapult for any further questions or requirements, but also directly to the TES Council or colleagues at Cranfield. So happy to take any questions. I know we're getting up against the break.
Thank you very much, Sam. It was very, very interesting. And we actually were discussing earlier that we wish we have this upload function that we can say thank you and give you a big upload for your presentation. So is there any question around? Anyone that would want to ask a question in person can raise their hand, or you can write the question on the Q&A. So I will start with one question, which is, it's a fantastic framework that you showed, and you demonstrated the impact that this can have. But I wonder how easy it is to transfer this kind of ideas into small SMEs, in which they might find it difficult to implement some of these ideas, let's say.
Yeah, so certainly to small SME, it may feel difficult to go and change the landscape, nationally and within your sector. There's a number of things that you can do. Certainly, just from a TES perspective, the PAS 280 publication is a quite practical guide, and already aware of companies, SMEs who started to adopt TES practices as a result of that. And there's a practical guide to look at how you can start to design. If you have design authority on the products that you're making, how you can start to design those against the TES framework. So there's real practical guidance there. If you're a manufacturer, then you can certainly start to look at thinking about, this is a natural direction of travel. How can you offer greater value to the supply chain that you're in and your end customers what might it mean to work towards greater flexibility in terms of working maybe smaller batch sizes, longer term contracts, and how can you demonstrate, because I think this coupling between through life engineering and sustainability is going to come together pretty strongly. As a manufacturer, it'd be important to think about how you can reduce your own emissions for the manufacturing processes you own, think about material sourcing and evidence those reduced emissions. So I think the PAS 280 framework offers a practical guide to companies of all sizes, depending on where you sit in the supply chain. And if you're in that manufacturing element of the supply chain, it can help you to build your strategy for the future direction and growth opportunities, but certainly start to think about where you can invest in innovations that drive down your emissions so that you can also compete not only on flexibility, agility, and of course cost and delivery, but also on sustainability.
Well, but that's a good point, because my question essentially comes from how much are SME thinking about these problems, which are real problems that they will eventually face, but do they have the scale to think about sustainability, or should be more the role of the government bringing to their scale these problems and these solutions?
Well, it's definitely a bottom up and top down. There is a role for government, and that's one thing I was advocating there. And there's the wider community to influence government to help with procurement, etc., and legislation. But no, as an SME, I think it may be difficult to start. It's not always top of the priority. And let's face it, right now, this year, companies of all sizes are having a very difficult time. Survival is the priority. But I think as you move from rebooting companies and surviving through the COVID crisis, and start to look at where are we coming back. It's not a normal bathtub curve where we're seeing a dip in the economy that's going to come back to where it was. There's going to be a rebalancing, I think, of growth sectors are going to be those that are driving a sustainability agenda. So as an SME, I think we're going to see growth opportunities for companies who are both pitching into markets that deliver net zero solutions, like the energy transport markets I've talked about, but also who can evidence that they have low carbon emissions themselves. That is likely to become a competing offering. And already this is a priority, public priority for some of the major aerospace and automotive companies who have market sector facing requirements to demonstrate low emissions. So building they're looking for support from people like the Catapult Network, from universities like Cranfield and others, and funding bodies such as Innovate UK, looking at some of the industrial strategy challenge fund programs out there like Made Smarter as a ways of accessing funding to de-risk the innovation to get started. So as companies are recovering, start to think about where those growth opportunities are and looking at innovation activities that reduce your own emissions and position you in growth markets that are operating to deliver net zero and operating increasingly towards a through life engineering services model. Perfect.
Thank you. Pavan, do you have a question?
Yes, it was more of a guidance, perhaps, Sam, given your expertise. We had the Test Council presentation this morning at a workshop. And one of the aspects for this, if we were to push the adoption of tests into industry, irrespective of the size, and if we say that they are quite new in the area, because it's quite a niche area, as you would say, where should they start? What would your initial guidance be to say? Because one of the things we do say is organizational readiness. So,
yeah. So which sectors to drive TES into?
I'm more thinking about, because it should adapt to a variety of sectors, variety of industries. And I'm thinking more of somebody who's coming in for the first time, perhaps they're from the academic side. Where would they start this journey? Because I'm sure they're already in the journey. It's just that they haven't joined all the dots together. So it looks like, for example, you showed the framework, which I know I've seen more often in larger corporations who have adopted tests as a strategy. Whilst if there are other people who want to adopt it, where would you start? Because there's always this learning curve. What's going to happen? How do we say this as a value proposition to the management as well? That's the lingo we are trying to say. Where do we start? How do we start?
Yeah, yeah, okay. So this depends. I mean, I go back. I think the TES value proposition, the slide I showed from the council, is a good value proposition around, extending the value through life, reducing the burden of cost and emissions through life. Now, of course, this is easy to address and recognise the value of if you have design authority or responsible for the service life cycle of an asset. So it depends where a company or an individual sits in the overall life cycle. One thing I think to deliver TED solutions, we need to start thinking about supply chains rather differently than just a procurement model where you procure for commodity resources. Okay, so if you're a manufacturer producing machine parts, it's a little bit harder to influence and drive the TES model. But if you're a company who's bringing, who has design authority over components you're bringing to market, it may be solutions around, let's say it's power electronic solutions, you can start to look at the value proposition for life extension and think about different business models. There are companies out there in automotive thinking about this already, actually. So a company called River Simple, a new startup looking at hydrogen vehicles, very different take on how you would design and operate vehicles. And whilst they don't talk about TES explicitly, Through Life Engineering is at the heart of the principle. They were designed for the full life cycle. They would even be responsible for the hydrogen that would fuel the vehicles provision, and they would be delivered on a service contract to consumers. So it's thinking about, for companies who have design authority, thinking about how you might reposition your value proposition to the market. And if you sit within those companies, how can you articulate that opportunity for market growth? Because this will drive market growth. It drives value for consumers and users. And it is entirely compatible with the increasing requirements for sustainability. I think there's an argument you can quite easily construct for your own management to drive corporate strategy. Anyone who wants help, I would say, look at the Path 20 framework, come to the TES Council, and come to partners such as Cranfield University, HVM Catapult, and many others who are associated here today to look at how it can be built. The council are looking to provide a broader toolkit and how to that sits built on the Path 280 framework to help people act and take advantage.
And if I just wanted to add one more comment, so the first step would be, as you said, approach one of us with the existing toolkit we can share, and perhaps think about from the company's standpoint what their value proposition is. So if they have that clarity, then perhaps before they come into our engagement, that would be a much more better.
Absolutely, yeah. Think about what that value proposition is. If there's a, I'd still say if there's a feeling that there is something there but not quite sure how to articulate it, we can help to identify that, but really understand the value proposition, not TES for TES's sake. Understand the value proposition, the commercial benefit and gain for a given organisation. But I think that the framework helps, and we can help companies and individuals understand that as well, potentially.
Thank you, Sam.
So there's one last question that it was posted on the chat with by Professor Sakao.
Yes.
Have you seen that one?
About the reference? Yep, the reference on the 40%. Yeah, that is one of the higher references that I've seen. It was from a consultancy group called Small World Consulting. They're associated with Lancaster University, a guy called Mike Berners-Lee, who's also a kind of popular publicist on the subject. And the chart I showed had slightly lower measures, but I was just showing the range, really. I think on that chart we were looking at more like 25%, 30% for fuel, for emissions, and it was about 25% perhaps for the manufacturer and fuel. So it's in that 25 to 4% range. There's a number of different publications out there, but most of them, I would agree, have a slightly lower number than that 40%. But when we move to electrification, we're talking into the 80s percentage of emissions associated with the embodied carbon of the product.
Perfect. So I think if there's any further comments, I think Professor Sakao can reach you on the table so directly afterwards. So let's.
Yeah, please do. Nice to hear from you.
Right. So let's close this session. Let me thank you once more, and we appreciate a lot your presentation. And we convene, let's say, 10 minutes from now for the last sessions of the day, which we will gonna have workshop 3 and 2 parallel sessions on room 1 and 2 with presentations from papers. Thank you very much, and see you in a few minutes.
Great. Thank you.